Swayam Prabha. Digital India. Educated India.
In the last class, we looked at an experiment which is called as 2D TOCSY, which stands for Total Correlation Spectroscopy, and we saw that it contains all the peaks from a COSY, but it has much more information, that is all the spins, all the nuclei in a spin system are coupled to each other, and that is revealed in a TOCSY. So, you can actually unravel a spin system based on a TOCSY experiment. So, now we come to another very important experiment known as 2D NOESY. As you can see here, the NOESY word stands for this acronym. The NOESY acronym stands for this word, that is nuclear Overhauser effect spectroscopy. So, Overhauser is the name of a person who discovered this effect, but it was not in organic compound, it was in a metal, but then the idea was he observed that polarization of one nucleus or one magnetically active nuclei or electron can be transferred to another nucleus. So, that is what we exploit in the case of chemistry or in biology, that two hydrogen atoms, if they are close by, means located in space closer to each other, then there is a possibility of transferring polarization from one to another. So, remember what is polarization? Polarization in NMR means the population difference. So, the population difference depends on the factors such as the gamma value, it depends on the magnetic field and the temperature. So, assuming that we are looking at protons only now, so gamma is same for all protons, temperature is same and magnetic field is same. So, what we are trying to do now is that one particular proton will have a given polarization is now transferred to a second spin through this effect known as Overhauser effect, and that helps us to find out which two protons are close to each other or they and interact through space. Okay. So, let us start from this. So, how does this experiment is carried out? So, before that let us understand this effect little bit more. So, this is what I said, nuclear Overhauser effect is what we study in NOESY. So, this effect basically is a phenomenon in which the signal of one hydrogen is affected if another hydrogen or proton is located close in space. Okay. Now, this is not just a presence of two hydrogens nearby results in NOE. What happens is you have to first irradiate one hydrogen. Now, the irradiation of that hydrogen disturbs the population level in that particular hydrogen. So, we saw that when you do not apply a pulse, that is known as Boltzmann distribution of population equilibrium, but when you apply a pulse it becomes equal in population. That means the two levels we say the word saturated, they are saturated means they are equalize the population. So, there is no more any population difference. Now, that polarization transfer, that polarization which is 0 now, it starts creating going back towards equilibrium when you remove the pulse. So, that the creation of this 0 polarization basically affects the neighboring hydrogen. If it is dipolar, it is coupled to this hydrogen. So, the polarization of this is affected by disturbing the polarization of this nucleus. So, why is this so? This is because they are close in space and there is an interaction known as dipolar coupling. So, remember till now in the case of COSY and TOCSY and also in 1D NMR, we only looked at J coupling, where J coupling is just an interaction between two neighboring hydrogens, either through 3 bonds or 2 bonds. So, that is because of the connection, the physical connection between two hydrogens. But this is not the case in this is not the only way of interaction between two hydrogens. The two hydrogens can also interact through space, means not through a bond, because they are close in space, and that is called as dipole-dipole interaction, because this is a dipole. Remember, the spins are all magnetic, so we call them magnetic dipoles. So, there is a dipole moment associated with one hydrogen and dipole moment associated with the second hydrogen. So, these two dipoles can interact with each other through the mechanism known as dipolar coupling, and this interaction affects the population of one hydrogen when it is irradiated. So, if this hydrogen is irradiated, it affects all hydrogens which are neighbor to it in space. So, you have to remember the point, we are talking about through space interaction, whereas those hydrogens which are very close far away, they are not affected. Okay. So, this is the main point in NOE, although we have not gone into details mathematical analysis of this interaction, but it as a qualitatively one can think of it that when the population of one hydrogen is disturbed through irradiation or inversion or any other mechanism, that disturbance is transferred to the second neighboring hydrogen. Okay. So, this is a very important word, transfer. So, whatever you do with one spin, that information or that perturbation is sort of transferred to another spin by which it is interacting via space. Remember, this is not J coupling again, this is not J coupling, this is only through space. That means, I do not need a bond here. Okay. So, for example, let us say you have a very large, let us look at it more carefully. So, let us say you have a molecule which has a structure like this, and there is a hydrogen here, let us say, and there is one hydrogen here. So, you see these two hydrogens are now close in space, but they are not connected through bond. Why? Because this bond is very far away, So, the only thing they are coming close in space. So, in such scenario, now if I irradiate or I disturb or I perturb or I invert, whatever I do with one hydrogen atom, population of the one hydrogen atom, that perturbation or disturbance will be communicated to this hydrogen, okay, or in the other words it will be interacting. So, this will now perturb this hydrogen also. So, although we perturb only this hydrogen also gets perturbed, or vice versa. If I disturb this hydrogen, this will be affected, because now they come very close in space. And now the question is, how much is the closeness, how much should be the closeness for them to interact. So, there has to be some limit. Typically the limit, as we will see here, is 5 angstroms, that 5 to 6 angstroms. So, if the two atoms comes within 5 to 6 angstroms, you will start seeing a communication between them in terms of dipolar or interaction. I would not use the word communication, although we are talking about qualitatively here, but the more appropriate word would be an interaction between the two hydrogens because of this dipolar coupling when they are less than 6 angstroms in space. Okay. So, that is a major important point here for as far as we are concerned. So, this is what is shown. So, if I have an hydrogen, any other hydrogen in the sphere in the radius of 5 to 6 angstrom will be affected by radiation of the nearby proton. So, this proton will be affected if this is perturbed, or vice versa, if this hydrogen will be affected if anything in its vicinity of 5 to 6 is perturbed. Okay. So, this is a major point here, that is through space effect, and the effect, as I said, arises due to dipolar interactions between two spins which are close to each other. Okay. And this method, so now if you see here, what has happened is, if I irradiate this hydrogen, I am affecting this hydrogen, the signal intensity of this. Remember, in NMR, signal intensity is all coming because of the population difference. So, if I change the intensity of one hydrogen, if I change the population of one hydrogen, the intensity of that hydrogen is affected because its population has changed. Okay. So, therefore, the intensity of the signal is what is monitored to get the information on the interaction. So, you see, if you have any hydrogen in this radius or of a sphere or a circle, anything within 5 to 6 is affected, which means that if I can find out which hydrogen if I irradiate and which other hydrogen is affected, then I get the information between those two, because they should be within now 5 to 6 angstroms. So, therefore, the distance information, the proximity, the information on the proximity of two hydrogens can now be obtained using this method of NOE. That is why NOE is a very powerful method in NMR, because it gives you the distance information between two hydrogen atoms, which you will not get by any other approach. Because if you see here, these, let us say, look at this picture again. This is a hypothetical molecule which has a very complicated shape, but there are two hydrogens which are very close to each other, and because of that, if I perturb one hydrogen, I see a intensity signal disturbance in the second. The intensity may go down or it may go up, either can happen, that we will see in the next slide. But this perturbation of each other now tells us that these two hydrogen should be now within 5 to 6 angstrom. So, you see we directly get the distance information, not the exact distance. Okay. We are not talking about exact distance here, we are talking about a rough estimate of proximity between two hydrogens which we get now because of the effect of each other. That information would not have come from any other method in NMR like COSY, TOXY and so on. It only comes from this experiment known as NOESY. So, therefore, NOESY occupies a very important place in NMR. In fact, for biological molecules this is very useful because biological molecules remember have a very complicated shape, and the distance structural information can only be obtained through this kind of an experiment, and that is one of the reasons why Kurt Wuthrich was given Nobel Prize, because he pioneered the use of NOESY for structure determination of biomolecules. Okay. So, that is why it occupies, in fact, all structure determination in NMR has to have a NOESY component, because no other experiment uses direct structural information as you get in NOESY. So, therefore, NOESY it is worth spending time on NOESY, reading about it more, and we will see this more and more as we go along in different applications. So, the detailed description of NOESY of course is beyond the scope, it is a lot of mathematics involved because we talk about dipolar interaction and so on, but I would suggest recommend this particular website which has this PDF which gives a very nice and detailed description, but it gives in a very simplified manner. So, you can go through this in addition to the books which textbooks which we have recommended. Now, as I said, this perturbation, that is which affects the signal intensity when we irradiate one nearby hydrogen, the resulting perturbation in the neighboring hydrogen can either result in an increase of its signal, we use the word positive enhancement, or it can decrease the signal, or it will have no effect, no enhancement. Of course, no enhancement means there is no either there are two reasons, one is the two hydrogens are not close to each other, or it can be by chance it has a particular value, we will see that, of what is called as a frequency which results in a zero enhancement, means no effect. So, NOESY can fall into any of these three categories in terms of the intensity effect, how it is affected by a neighboring hydrogen. So, this is where the matters, what parameter matters, whether you will get positive or negative, it depends on two factors. Number one, it depends on the spectrometer frequency. Spectrometer frequency means that what spectrometer are we working at 300 or 400 megahertz or 500 megahertz, etc. So, that frequency value is one component, and the second component which depends on the size of the molecule. Okay. So, size here we do not mean the molecular weight, because molecular weight is not really a good indication of size of a molecule. When we talk about size, we are talking in terms of a parameter known as rotational correlation time. So, rotational correlation time is the time taken by a molecule, or is an indicator of a time, the rotational tumbling of a molecule. So, remember all molecules in solution are not static, they are dynamic in nature. So, they are actually undergoing rotation, vibration and translation, but we use it also when it tumbles, we use our tumbling, that is rotation, rotational diffusion is the correct, more technical correct word. So, this rotational diffusion means rotation or tumbling of the molecule is characterized by a parameter known as rotational correlation time, that is in short tau c. So, this tau c is what is typically calculated like this. So, suppose you have a molecular mass, a molecule of 1000, let us say. So, then the rotational correlation time will be measured as follows. Let me give you how it is calculated. Roughly, this is not going to be an accurate calculation. So, tau c in nanoseconds is given as the molecular mass, or let me say weight, in kilodaltons divided by 2. Okay. So, let us look at this formula more carefully. This is a rough estimation of tau c. So, molecular formula, molecular weight in kilodaltons. So, for example, if you take a molecule which is 1000, that is equal to 1 kilodalton, 1 kd. So, 1 will come here. So, 1 divided by 2 is 0.5. So, the tau c of that molecule will be 0.5 nanoseconds. Okay. So, typically molecular sizes, except of course very small molecules such as water molecule or solvent molecules, when you talk about molecules such as organic molecules, compounds which are in the range of 500 onwards, they will have tau c in nanosecond time scale. Okay. But if you go to solvent molecules like methanol, water, it comes in picosecond time scales. So, all our examples which we will see or generally we come across are all in the range of nanoseconds. So, tau c is generally given value is in terms of nanosecond. Okay. So, what happens is whenever the spectrometer frequency, that is 2 into pi into the frequency, is multiplied by the tau c value, that is becomes equal to 1 or nearly becomes equal to 1, then at that kind of a, for that particular compound and that particular frequency, we will have no NOESY effect, no NOE effect, even if the two hydrogens are very close by. So, this is what comes from the theory of NOESY, which we cannot go into detail, but the point here is one has to look carefully that what kind of molecule you are using and what is the spectrometer frequency. So, for example, let us say you are working on a molecule which has a mass of 1000. Now, if you go to a 400 megahertz spectrometer and if you do this math, it is basically 2, remember omega is 2 pi into frequency. Okay. So, 2 into pi, that is 3.14 into 400 into the tau c. If you do this calculation, you will see it will be nearly equal to 1. Okay. So, because of this effect, what will happen is that particular molecule you cannot use NOESY for distance information. Remember, why are we using NOESY? We are not using NOESY for getting chemical shift correlation information, because that information comes from TOCSY and COSY. We are using NOESY for distance or proximity information between two hydrogens. So, therefore, if two hydrogens are proximal, they have to show a NOESY effect, but the NOESY effect becomes 0 if it happens that your molecule accidentally happens to be in this particular range. Okay. So, it is very important to keep in mind that what kind of spectrometer you are working at and what kind of molecules you are looking at, because by accidental, but you may happen that this comes close to 1. Remember, it does not have to be exactly 1, it can be close to 1 nearly, so let us say plus minus 10 or 20% also will result in a no NOE effect, and you will not be able to get any information on the distance or information in this molecule. So, now how do we come out of this? For example, let us say I have a molecule which I have to study at, which is I cannot change, this is what I am studying, and I have only one spectrometer in my laboratory. So, that means can I never do NOESY for this molecule? No, you can still do NOESY, provided what you can do is you reduce the temperature or increase the temperature. For example, remember tau c is what I said is a tumbling rate, means it gives you the rate of tumbling of the molecule. Tumbling means rotation and rotational diffusion. Now, that aspect is critically, it very much depends on temperature. So, if I reduce the temperature of my sample, obviously my tumbling will slow down, because the viscosity of the sample will go up and so on, and therefore, the tumbling will reduce and tau c will now decrease. Actually, tau c will increase, because the molecule will become a heavier molecule. It is not tumbling, means it is heavier, and if it is heavier, it has a more molecular weight. So, we have not changed the molecular mass. What we have changed is the apparent molecular mass, because the molecule now is tumbling slowly, it is behaving as if it is a bigger molecule. Okay. So, this is a very important point in NMR. By changing with playing around with temperature, you can play around or you can modify the tau c of a molecule, and this is very routinely used in biomolecules because we want to go to higher temperature or lower temperature for exploiting the favorable properties. So, if you go to lower molecular weight, in this case let us say you go to 5 degrees, this is remember this formula which I have shown here is typically for 20 to 25 degrees Celsius, but let us say I go to a very low temperature 5 degrees, the molecule is still not static, the sample is not frozen, and let us say we are looking at water sample. So, the molecule is not frozen. So, when the molecule is not frozen, it is having a slow tumbling because its temperature is low. So, it may happen that the tau c which was 0.5 nanoseconds in this case may become 1 nanoseconds. So, if it becomes 1 nanosecond, then obviously it is not equal to 1, this multiplication, then we have come out of this problem and NOESY will now work for your molecule. Or you can go to the higher temperature. If you go to higher temperature, let us say at 40 degrees or 50 degrees, it may happen your tau c becomes less now because it is tumbling faster, and that will make it behave like a smaller molecule, and the tau c will come down from 0.5 let us say to 0.25, and then again in 0.25 nanoseconds this will work because this product will not be equal to 1. Remember, omega is fixed, we are not changing the spectrometer, we are only keeping the omega fixed, but we are playing around with tau c. Alternatively, in your laboratory, if let us say you have 800 megahertz another NMR machine, then you can keep the temperature same, but change omega now. So, omega becomes twice if you go to 800 megahertz, and then there you will have that this multiplication now will be not 1, and you will be able to do NOESY. So, NOESY therefore critically depends on what spectrometer frequency you are working at, and it depends on the size of the molecule, which is indirectly reflected in the tau c value. So, the maximum, what is the maximum possible enhancement that you can achieve with all this, for given that you are not in this regime, that means you are not equal to 1, you are either below 1 or you are above 1. So, if you are above 1, we say that the NOE effect is negative, that means it is a negative enhancement, the peak intensity will decrease if I irradiate a neighboring hydrogen. So, the maximum the negative enhancement can be up to 100%. So, this is the theoretical limit which you can go up to, and the theoretical limit on the positive enhancement side is 50%. That means, if your omega tau c is basically less than 1, okay, if it is tumbling fast, if it is less than 1, then on the left side, that is on the positive side, we say that is called positive enhancement, and that you can go maximum increase of the signal up to 50%. So, this is a theoretical limit in which we work. Usually in the case of larger molecules such as peptides, large peptides and proteins, we are always in the regime of negative enhancement, that is omega tau c is much greater than 1, because remember tau c is depends on the size, and if you go to 10,000, okay, let us say 10,000, which is the size of a small protein, if you go to 10 kilodaltons, then your tau c will become 5 nanoseconds, that obviously if you multiply with the 400 megahertz you will get a large number which is much greater than 1, and therefore, we say that the negative NOE is active there, and there you will get a negative enhancement, whereas if you go to the smaller and smaller molecules you get a positive enhancement, but within these limits. So, NOESY experiment, how does it work? So, this is the pulse sequence. This is how we record. So, remember what I spoke in the last 2 slides, we talked about irradiation. So, that is called as a steady state NOE, means I am irradiating a signal, waiting for it to reach a steady state saturation, and then I am recording and then seeing the effect on the neighboring hydrogen. But that is not the only way to do NOESY. The typical and the 2D way, if you want to do a 2-dimensional NOESY experiment, we use the word transient NOE. That means, you are actually inverting the signal of a molecule. If you will see that now, we actually invert the signal, and that inversion of the signal is what is carried out, and that polarization inversion, remember this is inversion means we are inverted the population kind of. So, we have inverted the polarization, and that is transferred to a neighboring hydrogen if it is proximally located. So, that is how this is done, and that is called transient NOE. this is not same as saturation or irradiation. We are not irradiating a nucleus here, it is only RF pulses are applied. Okay. So, let us see how this works. So, you start from first 90-degree pulse as always, okay, and before this pulse the magnetization is along z axis. Okay. So, now we apply this pulse. When you apply the pulse, you have the situation which is we saw in COSY and TOXY, that the chemical shift evolution takes place of, let us say, some spin A. Okay. So, spin A has a chemical shift evolution omega A, which is shown here. So, I have brought the magnetization on the y axis, x axis, and that is evolving, means moving with chemical shift. Again it is decaying because of T2 and T1. After some time I will now apply one more 90-degree pulse. So, because it is in this axis, it will now go inverted to z axis, because it is equal to saying I have applied two 90-degree pulse, right. So, if I apply 190 followed by another 90, I have taken this magnetization to minus z. Now, during here this period there is no T2 relaxation. Why? Because there is no signal in the xy plane. Remember, T2 is for the xy plane and T1 is for z axis. So, there is no relaxation in the xy plane, only thing which happens is in the z axis. So, during that period, during the T1 relaxation, we give a delay, that is known as a mixing time. Okay. So, this is typically a long delay, depends again on the size of molecule and so on. So, let us say we give a delay of, is of the order of hundreds of milliseconds, okay, tens of milliseconds to hundreds of milliseconds. So, typically for proteins a value of 50 to 100 millisecond is used. For peptides, small molecules, we can go up to 300 500 milliseconds. So, during this delay, this period, what happens is that the polarization of one which is inverted, the spin A, gets the affects the polarization of C because of this effect known as dipolar coupling, and we use the word NOE. So, because of the NOESY interaction between two spins A and B, if they are close in space. So, please keep in mind we are talking about proximity here. So, these two spins are going, let us say, are close in space, less than 6 angstrom, 5 angstroms. Then any disturbance or anything I do with spin A population will be communicated or interacted with spin B. So, the population of spin B is also affected. So, population of spin B is affected, and that is now when I excite this, that means the whatever is the population of A has been transferred to B. So, whatever is the chemical shift of A also gets transferred to B. Okay. So, what we are basically doing is we are communicating the population difference whatever happens for A to spin B, and when does it happen? That happens during this period. So, during this period the population of A is changing because of its relaxation, and that whatever is the difference, the decrease in population is transferred, is affecting the population of B, and that is communicated to B, and that population difference also has this term, because remember whatever is the intensity of a FID, if you remember, it is related to the cosine into e to the power minus t. So, cosine omega t is also affecting the intensity of your peak of the FID, that is along with the population is transferred to spin B. So, when spin B is now excited with another pulse, the last pulse, then spin B starts evolving according to its own FID. Okay. So, now what has happened, this FID as we saw is now affected by two parameters. This has the information of this as well as how much has been transferred. Okay. So, therefore, these two effects are carried forward to B, and B starts now evolving according to its natural frequency, that is chemical shift. So, we have got now a 2D correlation between this peak and this particular spin. Okay. So, we will continue in the next class and continue with this. We will start off again looking at the mathematical little bit in more detail, and we will see how this information from one spin is communicated to other, and what is the type of spectrum which you will get now, and how does it compare with standard COSY and the TOXY spectrum which we have seen in the last class. So, we will continue in the next class with 2D NOESY.